now start our discussion on the properties of piezoelectric ceramics. This is the widest group of piezoelectric materials. Commercially the most important piezoelectric materials, with as I said, probably 90% in volume, and the number of different applications is based on piezoelectric ceramics. So which materials are there? Well, there is PZT, lead zirconate titanate, that we discussed in some details and will again. It is available in the form of single crystals, but only for research purposes. It is very difficult to make in the form of single crystals, mostly because zirconium oxide dioxide has a very high melting point, and you cannot buy them commercially. So if you are going to use them, that will be ceramics. Then there is a class of modified lead titanate. So that's lead titanate with either alkali metals such as calcium, strontium, barium, or rare earths such as samarium, gadolinium, and others, which are used on place on a site. Lead titanate, even though it is ferroelectric and has very large polarization and therefore piezoelectric, doesn't have that large piezoelectric coefficients. As an end member of PZT, obviously it has lower than PZT when used at around orthotropic phase boundary. And also lead titanate has a huge strain, about 6% at room temperature, and if you try to make ceramics, they will just shatter, break down by the time you cool them to room temperature because of the internal stresses. And these stresses are released partly by additions on a lead site. This brings down room temperature, and strain is reduced down to 2, maybe 3%. Still high, but ceramics can be made. These materials are also interesting because they have a very large anisotropy in piezoelectric properties. So D33 can be large, 50, 60, while D31 can be 0 and can even be positive. So small negative, 0, or a small positive value. And this is very interesting in some applications where you would like to reduce transverse piezoelectricity. Right now it's handled mostly by using composite materials, but in cases where ceramics have to be used, for example, there are acoustical microscopes and so on, where you want to have very high directionality of the sound wave, people sometimes use lead titanate based materials. Then there is lead metaniobate, which is interesting because it's a high temperature material. Then bismuth titanate is also high temperature material with extremely high Curie temperatures on the order of 600 to 800 degrees, but has very low piezoelectric coefficient. There is actually a relationship between a piezoelectric coefficient and Curie temperature in ferroelectrics, and as a rule of thumb, and this is not always true, but as a rule of thumb, if material has a larger TC, it tends to have a smaller piezoelectric coefficient. Then there are lead PMNPT, which are also available in forms of crystals, easily available, even though crystals are expensive. And the ceramics are interesting because they are still much cheaper and have higher properties than PZT. Then we have PMN, PI, and PT. These materials have a little bit higher transition temperature than PMN and are also available both in a single crystal and ceramic form. Then we have bismuth ferrite and bismuth lead titanate. Bismuth ferrite has a large Curie temperature, high Curie temperature, I think above 800 degrees. However, it suffers from a conductivity in ceramic form. And as a ceramic, it is not that useful. I don't think it exists in a commercial form. As a thin film, maybe, but not as a ceramic. However, in a solution with a lead titanate and addition of some rare earth oxides such as lanthanum oxide, it can get a very interesting high temperature properties, very large strains, and has been used for transducers commercially. It is possible to get devices with very special properties. And then you notice that almost all these materials contain lead except for bismuth titanate, because lead is toxic. There is interest in developing lead-free piezoelectric materials, and there are two main candidates. They are based on sodium bismuth titanate, solid solution with barium titanate, potassium bismuth titanium, and then addition of a barium and some other materials, and also potassium, lithium, sodium, tantalum, niobium solid solution, where the base material is potassium niobate, and then potassium is replaced with lithium and sodium. Lithium has a tendency to increase the transition temperature. Potassium and sodium add morphotropic phase boundary. Tantalum has an effect of decreasing the TC, and because of a large polarizability also improves piezoelectric response. However, these materials, even though they are very interesting from the point of view of a scientific point of view and are potentially interesting as commercially for devices, especially some niche applications, are not, as far as I know, produced widely commercially. I know of one Japanese company, Honda Electronics, which produces, I think, sodium bismuth titanate based materials. There are some thin films which are produced, I think, by a small company related to Megit in Denmark. Also high frequency transducers. We will discuss a little bit on that later on, but pretty much it's PZT for majority of the applications, and all these others are niche applications, really very specific application where PZT cannot work very well. So there is no, as of today, replacement for a PZT. There are materials that perform better than PZT, but it is only for some very specific applications. So why are so many good piezoelectrics based on lead, and what are the mechanisms? Well, this has been discussed in the past. There are some good papers that you can find. People are now using very sophisticated theoretical and experimental approaches to study. What we know is that lead is a highly polarizable atom. It creates hybridization of lead oxygen bonds. It has two lone electrons which are easily polarizable, and this is certainly a large part of why it is so. However, if you take a bismuth, which is also has some electronic properties which are similar to that in a lead titanate, in a lead, you don't get nearly as good properties as you do with the lead-based compounds. So it's an interesting thing that for 70 years now, lead-based material has been the most interesting, commercially the most successful material, and that there is no really replacement for it. It's not just toxicity of lead. There are other parameters. If you are looking at environmental effects, for example, then it turns out that niobium-based compounds are in fact not very environmental friendly. It's not toxic. It's a biologically compatible metal, but it is very expensive to extract from the mines. It requires huge amounts of energy just for extractions. So it is not easy to make always to make a decision what's good and what's not. I think we will have opportunity later on to still discuss this issue of lead-free materials. Now, when you work with ceramics are complex materials. They contain material itself within grains. There are grain boundaries. Grains are all oriented in different directions. When you apply electric and mechanical fields, the grains will respond to them. They will interact between themselves, and they are still not very good. There are micromechanics models that are starting to explain these interactions between the grains, but I still don't think that I can just tell you I'm using PZT of this and this composition, and I want this grain size predict to me the properties. I don't think that it is easy to do. And just to show you some of the reasons why interpretation of experimental results is difficult. Here is piezoelectric coefficient D33 and D31 for a PZT. So it's one rhomboedral composition, and we measure piezoelectric coefficient as a function of grain size. So we prepare ceramics with the same chemical composition with a different grain size. And you see that the piezoelectric coefficient changes by a factor of almost 50%. So this is amazing. Just the grain size. Now, how does a grain size do this? Well, there are several things. First of all, the domain walls distribution and efficiency of polling are different for a small and a large grain sizes. But you see here that very small and very large grain sizes actually have similar properties. So that cannot explain everything. We know that the grain size determines the domain size, and that mobility of domain walls, domain wall motion, depends on the grain size. And this is well understood. But this evolution with the grain size and this peak is not very well understood. If it was going something like this, it would be easier. Well, one thing that needs to be understood here is that when you change a grain size, when I'm plotting this correlation between piezoelectric coefficient and the grain size, I'm actually telling you that the grain size is the only factor that is affecting piezoelectric coefficient. And that's not true. How do I get different grain sizes? Well, I get different grain sizes. For example, I can get it by sintering material for a longer time at a higher temperature. And that will have other effects. That can change quality of the grain boundaries, that can lead to lead loss. at higher temperatures and for a longer time because lead easily evaporates. Once you put ceramic at room temperature, oxides are very stable. Lead is not going to get out. But at high temperatures, you prepare these ceramics at temperatures between 900 and 1200 degrees. And I think you all know what sintering is. So this is a sintering temperature. The concentration of defects can change, and that can have an effect. So there are different things. It's not easy to explain these, and one has to be very careful when talking about causes and effects and correlations. If you have a correlation, that doesn't imply that there is a causal effect. Actually, here what we found out is that during the processing, these grains around 4 microns actually had a best mixture of zirconium and titanium inside, and were closest to morphotropic phase boundary, while those grains with very large and very small grain sizes had one of them had a little bit of precipitation of zirconium. For example, you had a core shell structure in which there is more zirconium inside the grain than outside the grain. So it's a question of processing, not property really of PZT. If you measure piezoelectric coefficient as a function of temperature for different PZT ceramics, you get that, and the only difference here, the zirconium to titanium ratio is here the same. The only difference is doping. And you find out that at room temperature, there is a huge difference by factor of 5 in piezoelectric coefficients, while when you go down to 4 kelvins temperature of liquid helium, all of these ceramics have exactly the same piezoelectric coefficient, or very close piezoelectric coefficient. Now, it turned out that here we are talking about domain wall contributions to the properties. Domain in those materials where they can contribute, and you will see later on, we will discuss in details, so-called hard PZT and soft PZT. In hard, domain walls cannot move very much, so these would be hard materials, this would be soft materials. So at high temperatures where domain walls can move, you have a large response in the soft materials. But once you go to 4 kelvins, these domain walls, these interfaces cannot move that much. Everything is frozen. And then you have just response of lattice, just vibration of atom around the equilibrium position without having these big jumps over the potential barrier of for example, titanium, basically locally switching from one ferroelectric direction to another. Another difference, for example, again in so-called soft and hard PZT, is that piezoelectric coefficient here as a function of pressure amplitude is much more stable in hard PZT than in a soft. While you like to have a large piezoelectric response, you don't want it to change too much with the field, because then calibration of your instruments becomes difficult. This is actually something that we already covered, and this is due to domain walls, this nonlinearity. And in fact, what we have is that in soft materials, domain walls can move a lot. In hard, they cannot. And we will discuss mechanisms of that. That's actually, apart from a morphotropic phase boundary, one of the most important concepts in piezoelectricity, soft and hard materials. And then finally, there are structural effects. So again, PZT, but different ratios. So here you have zirconium-rich, MPB composition, and tetragonal titanium-rich composition. And we are plotting properties as a function of driving pressure normalized to the first value. So the rhombohedral D3 of a rhombohedral phase is actually smaller than D33 at MPB, but we are plotting them all here equal at lowest pressure. We just normalize it like that. However, you get that nonlinearity is biggest in rhombohedral, then in MPB, and much bigger than tetragonal materials. And this has to do with the domain wall motion in a rhombohedral material and relationship with the strain and so on. Next, I would like to discuss in rather some detail differences between soft and hard piezoelectrics. When you are buying piezoelectric ceramic, you will basically have a choice between the whole catalog of compositions, and in general, they are classified according to whether they are hard or soft materials. So the mechanisms of softening and hardening are very interesting, and we will spend some time discussing that.